Welcome back to our Algebra 2 series. Today we are up to section 5.4 where we'll be looking at common logarithms. This is a continuation of comparing logarithmic functions to exponential functions. So if y is equal to log base a of x, we can also say that x is equal to a to the y power, because a logarithmic function is the inverse of an exponential function. Let's take a look at this example. Log of 23. But what's the base? There's nothing down here to tell us what base we're using. Well, it turns out when no base is provided for a logarithm, it is a common logarithm. That means we are working in base 10. Base 10 is a number system that we know and love. We use 0 through 9. We use 10 different symbols to represent our numbers. So we would just write it as log 23. And if we were to put this into a calculator, we'd find that the log of 23 is 1.36172 and a bunch of nonsense. So what that means is 10 to that weird number is equal to 23, which makes some sense. 10 to the 1 power would be 10, and 10 to the second power would be 100. So 10 to the 1.3617, the answer would be somewhere between 10 and 100. What about the log of 5.24? But we can't use a calculator this time. What are we supposed to do? Well, we know we have a common logarithm because the base isn't listed, so we know we're in base 10. For common logarithms, we can use a known table of values, and it looks something like this. For this example, let's look at the small section of the table. On the left side, we have x, and we have 5 point and then the 10th place, and across the columns would be the 100th place. So we find 5.2 and scroll our eyes over to the 4 to get 5.24, and the answer is 0.7193. So the log of 5.24 is 0.7193. What about the log of 52,400? Well, most common log tables contain x values from only 1 to 9.99. But that's all we really need. It's our turn to be sneaky. So let's rewrite this expression in scientific notation. As a quick reminder, scientific notation is a single point and then a decimal times 10 to some power. So for example, 4,500 would be written as 4.5 times 10 to the third power. Yes, this is scientific notation. We can't write it as 45 times 10 squared, even though that equals 4,500, because we have a 2-digit number here. So going back to 52,400, we can say that this is the log of 5.24 times 10 to the 4th power. If you remember, when you're taking the log of two things being multiplied, it's equal to those two separate logarithms. So we can rewrite this as log of 5.24 plus the log of 10 to the 4th. Using our table fun, we know that this first part is 0.7193. And we also remember that when we take the logarithm of something with its own base to a certain power, we end up with that power. So the log of 10 to the 4th is just 4, because we're in base 10. So the answer is 4.7193. As you can see, there are two components to this answer: a decimal and a whole number. The decimal portion, found from our common log table, is known as the mantissa. Yes, I guess we're just making up words now. The whole number portion, which we found from the power of 10 in scientific notation, is known as the characteristic. And the answer contains both the characteristic and the mantissa. But this isn't always the case, of course. Let's look at this example, the log of 0.0538. First, we'll rewrite it in scientific notation of log of 5.38 times 10 to the negative 2, because we're moving the decimal point the other way. And because we're taking the log of two things being multiplied, we'll split it into a sum of two logs. And if we used our table of fun, we'd find that the mantissa is 0.7308. And using our log fun, we know our characteristic is -2. And if we add those together, we get -1.2692. But neither the mantissa or the characteristic have been preserved. So what do we do about that? Well, there are two options. The first is to leave it separated like this with some brackets, where the mantissa is left alone and the characteristic is a negative number. This is how I would recommend going forward. However, some math books have a different proposal. Because we're in base 10, we need to think of that -2 as some other value minus 10. So -2 would be written as 8 minus 10. We could bring that 8 out and have 8.7308 minus 10. So in this version of the answer, we still have the mantissa, the decimal portion, of 0.7308. And because we have this weird minus 10 hanging out at the back, we know that 8 minus 10 is -2. But I prefer to keep it separate. It's very clear to see what the characteristic and what the mantissa is with your answer. Let's jump over to the whiteboard and do some examples. Okay, we're going to just do a few logarithms. Make sure we're on the screen and in focus. Good enough. All right, we're going to say log of 2.46. Now there's nothing down here, so we know we're in base 10. So we have a single number and some decimals. So we'll have to go into the table to see what that is. So here is the table. If we look at the x value of 2.4, and scroll over to 6, you can see that the answer is 0.3909. 0.3909. And this is our mantissa. Next, we'll do the log, again, base 10, but we don't need to write it because it's a common logarithm, of 1.07. Let's go back to the table. So starting on the left, the x value is 1.0, and we go all the way over to the 7 column. The answer is 0.0294. 0.0294. All right, let's do one with a slightly bigger number. Log of, let's say, 3,870. Okay, so we got a big number here. We need to break this up into a sum. So to start, we'll put this in scientific notation. 3.87, I guess 0, times 10, 1, 2, 3, to the third power. Give myself more space than I needed here. So the third power, 1, 2, 3, 1, 2, 3 is 3870. That's what we have. So this breaks out into the sum of log, again, base 10, but we don't need to write it, of 3.870 plus, because we have a multiplication here, the log, again, base 10 of 10 cubed. So for this first part, we need to go back to the table. So at the very bottom of the frame, we've got our 3.8, and we need 3.87. So if we look at 3.87 and go all the way to the 7 column, we have 0.5877. 0.5877. And for this one, we're taking log base 10 of 10 to the third power. Whenever you take the log of something with its own base, all you're left with is the exponent. So we have just a 3. So we can combine these into 3.5877. The 3 is our characteristic, and the 0.5877 is the mantissa. All right, let's clean this off and do one of those weird ones with the weird mantissa. All right, we'll up here in the corner, mostly in focus. We'll say the log of 0.0702. So let's rewrite this in scientific notation. This would be the same as saying the log of 7.02 times 10 to what power? Well, we need to move it 1, 2 spaces. So -2 power. And this would be the same as, we'll split this up right now into a sum, the log of 7.02 plus, because we've got a multiplication that turns into two things being summed, the log, again base 10, but we don't need to write it, of 10 to the negative 2. So for the first part, we'll go back to our fun table. So 7.02, we'll go to the 7.0 row, and the 2 column gives us an answer of 0.8463. Right about there somewhere. 0.84, no focus. Oh. So this was 0.8463. It's our mantissa. So we're taking the log of 10 with base 10 to some power, and all that just turns into the power. So I'm going to write it as plus negative 2. And I guess we can see these are all equal. So we have our mantissa and our characteristic. So this is how I would normally leave it. But let's write it in the weird way, just in case that's how your math class is teaching it. So this 2 needs to be rewritten as another way of saying 2, or negative 2, with a 10 in it. So we're just going to rewrite it as 8 minus 10. Because we're in base 10, that's why we use a 10. And this is still 0.8463. And then we just bring the 8 out in front of the mantissa. 463 minus 10. So whenever you see it written like this, you know you have to take this 8 minus 10 to get the characteristic, and you're still left with your good friend, the mantissa. That's it for today. It's a pretty short section, but we'll see you next time.